Hi everyone, welcome to today's video. Today we are going to understand how the x86 assembly works. So today we are going to build a high-level mental model of this x86 assembly. Basically, we'll start from a tiny C program, then we'll look at the assembly that the compiler generates, and we will understand what does different line means, and then we'll deep dive into sample x86 instruction. So basically, today's goal is all about getting comfortable reading assembly code. So before we move on with x86, maybe let's do a quick recap of how the compilation process works. If you remember, we can have multiple C file or header file, then it goes via C preprocessor, and then it expands all the header information and necessary information. Then you have the compiler, which generates the compile code, and then you have the assembler, which generates the object file of each code, and then you have a linker in addition to the library and all the object file. It basically creates a binary executable, right? So before we move on to x86, let's see how the output of the compiler looks like. For today's demonstration, I'm going to follow the same example we are seeing so far. It's a simple hello world program where we're including something, and then you do a puts with hello world, and then you return 0. So I'm going to output right now within using this thing GCC, then minus S, and then M assembly is equals to Intel. I'll explain later in this video what this is, and then I just feed my C program. So the output of this particular compilation process is hello.s file, which is nothing but a intermediary output of the compiler, which basically tells assembler what to do. There are many things in this particular hello.s file, which is supposed to instruct assembler about a few things. So to that, basically, there's a lot of information, but I wanted to mention four definition. First thing is basically instructions. So instructions are basically the actual operation the CPU executes. So for example, this is an instruction that moving RX to RDI, right? And then you are supposed to call this puts function. So these are like raw information which actually execute by the CPU instruction. Apart from that, there is another definition which are called directives. Directives are basically command to the assembler. These are not like real CPU instructions. So directives can be maybe this dot string, this dot section, dot text. Like these are not the information you will actually find in the real executable code. These are for the assembler. So this basically tells assembler, okay, if you have a string, you should you should put under this dot string. If you have this read only data should belong to this particular section, etc., etc. So we learned about instruction, then directives, and then the third thing is called labels. As the name suggests, labels are basically symbolic names for positions in the program. So, for example, you can see the main, the type is basically main. So, this main is basically a symbolic representation of the main function, right? And then you can see dot global main, that means the main should be visibly globally throughout the program, something like that. Right. Then there is this other thing which is not actually present in this .s file are called comments. So basically, whenever you have like hash something something, so basically those are meant to be comment, and those are just meant to be human. So, but the assembler simply ignores them. So now we saw the four common definition in this input of the assembler. One is instruction, then you have directives, then you have labels like dot, like main, etc., etc., right? Like main, and then you have comment, which is not currently present. There are a few things also you need to understand as this code and data separation. So compiler has this predefined notion where the code should go, where the data should go, right? So for example, a dot arrow data is supposed to be a section where only the read-only data should go, and then there should be a section called dot text which is supposed to take this CPU instruction, something like that, right? So compiler tries to ensure or give all of this information to the assembler so the assembler can put the data wherever it is supposed to go, or the CPU instruction it's supposed to go to text, something like that. But x86 doesn't actually enforce this particular notion. You can have code and data in any way you want throughout your binary. That is what makes the x86 a bit tough too, right? So far what you see is this whatever output the compiler is giving and whatever is going into the assembler, like, right? But when you actually compile the binary, so for example, I'm compiling hello.c and I am just creating this hello object, right? If I just write, you can see the print also. And now if I actually disassemble this, so for example, we have seen this tool object dump minus d, then if you do hello, now let's save it to some file. .asm is just my extension. It doesn't have to be .asm, right? Now, if I open this, this is a bit separate from what you have seen in that hello.s, right? Because that was not a decompilation of the full binary. This is the decompilation of the full binary. Similar information you can observe here also. So for the example, there is just directives like .init, .plt, and there are multiple compiler defined functions, and then you also have your main function. And see, you can also see an example of comment, like anything followed this hash is a comment, right? um, so so what we know from with this object dump is we can disassemble the binary using this tool, right? But there are two important syntax of this assembly language. One is called AT&T syntax, and then the second one is called Intel syntax, right? So I want you to observe a bit closely. So let me do it here. So object dump by default basically follows this AT&T syntax. But if you want to have an Intel syntax, then you can do object dump minus d hello minus m Intel. And let's call this hello Intel.asm, right? Now, first, let's look at how AT&T syntax looks like, which is basically in my hello.asm. Let's do a cat and let's focus on the main function. So the AT&T syntax is basically the only difference is where the source and the destination operand lies. Okay. So in AT&T syntax, the first operand, so let's look at this move operation. In the AT&T syntax, the first operand is basically your source and the second operand is basically your destination. So what does this instruction means is move content of the RSP to RBP, right? This is AT&T syntax. Now let's look at the Intel syntax. So if you look at the Intel syntax, this is completely opposite. So previously it was move RBP to RSP. Right now the destination is at your left. So RBP is your destination and RSP is your source. So this is the only difference I could observe from AT&T and Intel syntax, and looking at the code, you should know. Oh, there are a few more difference to be honest. So for example, if you again go back to the AT&T syntax, with registers, you have this percentage symbol, and with immediate or any kind of hexadecimal number, you'll have this dollar signature. Uh, wherever in the Intel syntax, it's not there. You do not see any percentage with this. And similarly, you don't see a dollar sign with any kind of immediate value. So whenever you see without the registers without the percentage, you know it's an Intel syntax. And whenever you see it with the percentage and the dollar with the constant, then you know it's an AT&T syntax, right? The underlying code remains the same, is just the way people represent it and how they read it. So now looking at any kind of instruction, you should know what kind of syntax it is following, and now you know how to read this, right? So be having said that, now actually let's dive into this x86 instruction. X86 instruction can be in two level. First is assembly code level, like I am showing you right now. So let's say there is this move RBP RSP. So the syntax is you will have your opcode, and then you will have your depending on the syntax, either your operand value, source operand, or the destination operand. Now, the operands can be registers like RBP, RSP, or it can be some kind of this memory location. That means whatever value you have at the RIP, then you add this number, you go to that particular memory address, and then you actually load the content of the memory. All right. Now this instruction is LEA, is doesn't really load the memory, it's loading the effective address of that particular memory location. So basically you're loading the address, not the data in the memory itself. But whenever it's not LEA, then you're actually loading the value. So for example, you have this move instruction where you're moving this one value to this particular, whatever value in RIP is, you add this offset, and then you save the one to that particular memory location. This is the assembly. This is the assembly level structure of the x86 instruction. But there is another structure which is called like machine level structure. So let's try to see how the machine level structure looks like. Again, this is the same book we have been following. This is practical binary analysis book, and this is how the machine level structure of the x86 instruction looks like. X86 instruction is of variable length, and that is what makes the disassembly very hard. Sometimes it's 1 byte, sometimes it's 2 bytes, so it has this whole range of 1 byte to the 16 byte. So the first 0 to 4 optional bytes are called prefix, and then 1 to 3 bytes, depending on what kind of opcode you are using, is basically opcode. And then there is this special thing called addressing mode, or ModReg RM. So basically it's tell you like whether your operand is registers or memory, and does it have a scale based index or displacement, which should come follow. And then you have this SIB byte, which is called scale, base, and index. So think about it when you try to access an array, right? So what you do AI plus 4, right? So A is basically your base of the structure, and then you have the scale and the index is basically I, and scale is basically you just move 4 byte at a time, something like that. So the similar structure also lies in this SIB byte. So using this 0 to 1 optional bytes, you basically mention that. And then if you have an explicit displacement, like from this particular address, go to maybe 20 byte offset from there, something like that, you can mention that number in this optional 0, 1, 2, or 4 bytes. And then you have immediate value. So if you want to put like constants like 0, 1, 32, whatever, then you put it in the immediate thing, right? So to note that these are optional bytes, so depending on what kind of instruction you are going to use, so you'll have this multiple options there. So for example, let me try to show you a few example from our particular hello world, and maybe with something else for the SIB. and let's try to compare side by side how actually it looks like, right? So let's look at the simplest one byte instructions, which has nothing but opcode. So that can be, let's see if we have a no op. Yeah. So, okay. Yeah. I think you don't have to look at no op. So basically, you can see this instruction and its particular machine code value C3. C3 is basically opcode for the return instruction, and then you can have also no op instruction there. So no op, basically, I think the opcode value is hex 90. So if you have like hex 90 in your disassemble code, that means it's no op, right? Then you can have a different kind of instruction. For example, move RBP to RSP. So this move operand will be encoded using this 1 to 3 bytes. And then you will have this ModRM bytes, which basically shares that your source operand is this, your destination operand is this, both are registered, and you don't have a scale base index, and you don't have a displacement or immediate. Let's try to see the scale base index maybe with this particular example. So I have a very simple for loop example for you. Okay, this is not visible. Let's see. Dot C, right? So this is a very simple for loop I was mentioning about, right? So you have your 5-element array, and then you are trying to access this array I, right? And with I plus 1 every time. And if you just basically, I have already disassembled it. Let's look at the ASM file related to this. So I want you to focus on a very particular instruction. So this is the instruction where what this instruction is doing. So this is an Intel syntax, and we know the right hand operand is basically the source. So this is basically our source, and this is our destination. So what this source is saying that RBP is basically the base register. So you can think the RBP is maybe containing the base of the array. And if not the base pointer, but anyhow, somehow you're going towards the base of the array. And then this REX is basically called index. That means that I, at this point of the time, I want to access maybe A2, A3, something like that. And then the scale, so basically each value is basically a 4 byte, so you move 4 byte at a time. And then you have this displacement, right? So why the displacement is needed? So basically RBP doesn't contain the start of the array, it is the base pointer, and if you do -20 along with the base pointer, then you have your the base address of the array, and then you, whatever index it is, you just access that particular byte, right? So this instruction you are seeing is basically assembly level, right? But similar thing has been encoded here in this binary numbers following the same structure of the x86 instruction. So today we'll just have an high level introduction to this prefix opcode, ModRM, SIB index, displacement, and immediate. In the later part 2 video of crash course of x86 assembly, we'll look into details what each byte means or what each bit means and how it is actually correlated to it. But in general, even if you don't really remember the machine level x86 instruction, I think assembly level x86 instructions should be pretty enough for actually, go through the assembly code and understand what it's doing. Having said that, now the next important thing is how many register does x86 architecture have, right? Let me zoom it a bit and then we'll follow. Yeah. So x86 also have two kind of mode, 64-bit architecture and 32-bit architecture. For the 64-bit, you have a 64-bit register, which is you have many registers like RAX, RBX, RCX, RBI, RBP, etc., etc., going towards R8 to R15. Now, you can also use the lower 30-bit of the register and use it in legacy 32-bit x86 system, and the lower 32-bit basically called EAX, EBX, ECX, and so on. Similarly, you can also use the lower 16-bit, which is called AX, BX, CS, DX, etc. Similarly, lower byte, AL, BL, and the second byte, AH, BH, CH, and DH. Before we move on to actually looking how many important instructions there are, which you basically need to understand how x86 code works. But before that, there are a few special register. So for example, RX. So whenever you are returning something, your function has, computed everything and you are supposed to return something, that value is actually stored into Rx, and then your function return, and the caller function knows, okay, return value is in Rx. So those are some kind of special registers, right? Then there is this RSP, which is basically stack pointer, and then you have the RBP, which is base pointer of this particular function, and then there are some more register to actually manipulate the strings and so on. And then you have some general purpose registers to store and compute, etc. However, this is not a strict setup. Sorry. With increased optimization, RX can do many stuff. It doesn't have to be accumulator. So you can not you like x86 architecture can use them any way they want it to be, right? Um, okay, so we learned about x86 operation. We saw that there are AT&T syntax. We saw there are Intel syntax. Then we saw the assembly level where you have the operand. Sorry, you have the opcode followed by two operand. The operand can be registered. The operand can be immediate value. The operand can be memory address itself. Right now, let's look at like a few very important instruction of the x86 architecture, which you will commonly see. There are many more, but I think with a basic understanding of this instruction, you will be able to read a particular program, and we'll actually show how to read it today too. So let's look at the common instruction. So these are very important instruction, and we'll go through one by one. So first is basically moving the destination to source. I think looking at this, you already know this is Intel syntax. So basically, this is the second operand is operand is the source, and the first operand is the destination. So whatever there is in there, the source operator, and you are supposed to move it to destination. So after this instruction has been executed, the destination should be equal to source. Then you have this exchange operation, which is basically swap destination 1 and destination 2. Then you have this special instruction push source. So whatever value is there in source, you basically push it to the stack. But this operation has an after effect. The RBP, as you have pushed, the base pointer will, move. Not RBP, sorry, RSP, the stack pointer. The stack pointer will, decrement and move one position away. Then you have this another special thing, which is pop destination. So whenever you're popping, you need to readjust the RSP2, right? Then you have a simple add destination source, which destination is basically destination plus source. Then you have the subtract. Then you have an increment the destination. Then you have decrement the destination. So destination will be equal to destination minus 1. Then you have this neg destination, which is destination equal to negative of the destination. Then again, you have this special instruction where you are comparing the source 1 and source 2, and depending on that you have status flags, right, like overflow, zero flag, etc., right? You set the status flag. And why this is important, so depending on the comparison, some flags will be turned on, and later when you have this branch instruction like jump if it is less than, or jump 0, so you can cross check with the status flag and then you jump accordingly. You can also have this logical or bitwise operation like AND, OR, XOR, NOT, and then the test one. So again, depending on the comparison or the end of the source 1 and source 2, you will basically set some status flags, and then again when you will basically take a jump or something, the conditional jump, not the unconditional jumps, you will check the status flag and then accordingly take the decisions. So then you have unconditional jump. Basically you just simply jump to the address. Then you have this call address. Whenever you're calling a function, you do this call address. Then whenever a function is done, you wrap it up and you return to the caller, right? um, Now these instructions have some more side effects. So whenever you're going to call an address, so basically you push the return address on the stack and then you call the function at the address, so that once you're done with the calling function, you remember where to return, right? And then whenever you do, basically you already have pushed in the call address instruction execution. Now you pop that return address from the stack and return to that particular address. Then you have this another instruction called syscall. Basically here you just go beyond the user level to actually kernel level mode and perform any kind of system calls. Then you have conditional branches, as I said, based on the status flags, right? So here JCC address is the common format. CC is basically your condition. It can be a different condition. For example, JE or J0. So jump if the zero flag is set, right? Then you have JA, which has its meaning jump above. Jump if destination is basically greater than source in your last comparison, and it has to be unsigned. Then similarly you have jump below, then jump greater than, jump less than, jump greater than equal to, jump less than equal to, and JS is basically jump if the last comparison set to sign bit, meaning the result was negative, right? Then you have this special instruction, which I already told you about, load effective address. So basically load memory address into destination. So whatever the source variable is, whatever address is holding, then you just load it to the destination. And then this special instruction called no op, which basically does nothing, but you use that for padding, or compiler use it for alignment for better optimization of the loading. I think these are bare minimum x86 instruction, the assembly level mode we need to understand. We need to know to actually, to actually understand how to read the assembly language. Having said that, let's now try to read side by side how does an assembly code and C code looks like. For that, let us first start with our simple hello.c, right? Sorry, not the code. Let's do it using gedit. No, it's very small. Let us detach the terminal. Then zoom it a bit. So what we're trying to do right now, we are trying to learn how to actually read this assembly code and the C code side by side. So similarly, let's clear this window and let's open the Intel version of the assembly level, right? This intel.asm. Okay, we'll have plenty things going on, but we'll mainly focus on this main function, right? Because we're trying to learn how the assembly code main function looks like the C code main function. So let's look at the C code first. What it is doing, it is basically putting the hello world on the console for the print, and then it is doing nothing, returning 0. Let's look at line by line. This is a special instruction. We'll skip it for now. This is actually implemented for control flow integrity, but it's a high level concept. We'll go it later. So first thing it does is put the base pointer there, right? The RBP, whatever RBP was there with the previous function, you push it there, and then you move. This is source. move RSP to the RBP. These are called function prolog. If you go through every function, you will see it. It is doing some kind of setup to make sure it has its own, stack frame, and within the stack frame, it does all of this operation. Now what it is doing the LEA, loading the effective address of RIP and adding with this particular offset. Then whatever this memory thing is pointing to, you take the address of that thing and you loading to the RX. So what does it loading? So this RIP is basically holding some address of our hello dot world string. So this string is actually stored in the RO data. This RIP has some kind of RO data address, and then when you offset with this particular hex EAC, it's basically give you the effective address of your hello world string, and you just load it to RAX. The address of the string, not the string itself. Now you load this particular thing to this RDI register because your puts function basically expect you in that particular register. And then you call this particular thing, which is basically your puts function. But this is a dynamically linked function, and we have already seen in our lazy binding video how actually it gets converted to the libc library. But for now we can assume, okay, this is calling the puts function. Now once this puts hello.world is done, now then you have this return 0. So as I already mentioned, the return variable are supposed to go into the EAX register. So you come here and you see, okay, 0 is actually moved to EAX register. Then you are popping the RBP to actually know where to go, right? The return address. Then no, you're just popping the base pointer you have pushed, and then you have your return function, which is basically popping the return address, and then you are moving to from wherever the main function has been called. Make sense? Now this was a very simple one. We saw that, okay, the hello world was there in the read-only data. You load the effective address, you pass the address to the post, let puts to what it does, and then you return 0. Let's try to look at it a bit hectic example, right? But it will not as hectic as a real life program, but still. Let's try to look at this for loop dot example dot c, right? Before we look into it, maybe let's do the disassembly, and let's do it in Intel format. For loop example dot asm, and then you do cat for loop example dot asm, right? Now it has a lot of information, so let me just zoom out a bit. Again, we'll start with our main function. As I said, this is a special instruction to make sure integrity, the control flow is actually not hampered by some attacker or hacker. And then you have this prologue, and you're subtracting the RSP from this hex 30. So basically right now you're dynamically allocating some stack frame for this particular main function. Now when we go back to the C program, what it is doing, basically it has this 10, 20, 30, 40, 50, assigning it to a local variable array. Remember, local variable are stored on the stack. Then you have this sum variable, which is 0, and then using the for loop, you're basically summing each number, and you're printing the whole sum, and then you're returning 0. Yeah, so now as I said, these variables are basically local variables, right? So if you look at the hexadecimal value of 10, right? So hexadecimal value of 10 is A, right? Now you know that so now you know, okay, RBP minus 20 is basically my first element of the array, then 14 for 20, E, then 28. So these 5 variables you can see is basically we are initializing the local variable array, right? And then we also have 2 more thing, one for sum, and one for this int I equal to 0, right? Right now we don't know which one is sum, which one is I, but we'll figure out it later. Then what you are doing, you are jumping to 11C7. So 11C7 is basically here. Basically, you are comparing it with 4, right? Because you're supposed to run from 0, 1, 2, 3, 4, right? So if this comparison is satisfied, then you move back to the for loop, else you actually go exit. So let's say this is satisfied for the first time and this is less than equal to, that means your I value is basically still less than 4. So now we know, okay, RBP minus hex 24 is basically I. So now you can confirm, okay, RBP minus hex 20 is 28 is basically your sum variable, and RBP minus 24 is your I variable. Now you compare it with 4, okay, still less than, so you move back to 11B7, and 11B7 is here. Now what you are doing, look very closely. RBP minus hex 24 was your I, right? So you take it, you move it to EX register. CDQ, it's nothing but it just fills the upper 32-bit with 0, and now you can access the EX register with RAX. So basically after this, your RAX will have RBP minus x24, which is I. Now you see RBP, so your array starts from RBP minus hex 20, right? So RBP minus hex 20 is basically start of your array. RX has I, and 4 is basically your scale, right? Now this thing is basically currently RAX 0. So pointing to the first element of the array, you are loading the first element of the array to your EX register. Then you are adding it with hex 28, which is nothing but your sum variable. And then after adding, the sum variable is updated, right? We saw add destination sources, destination equal to destination per source. Now this sum variable will have the updated value, and now you are adding 1 to your I variable, which is nothing but RB minus 14, and then you are comparing. If the comparison is successful, you will again go back to the beginning of the loop, sorry, and then you'll do the rest. Then at the end, your comparison will be unsuccessful. You will go down to this particular instruction. What this instruction is doing, so after the loop, what we're supposed to do, we're supposed to print the sum, right? So first thing you're doing, you're loading the sum value to the EX, and then you are again moving the EX to ESI, and then you are doing again the load effective address of with reference to this particular RIP, which is pointing toward this read-only data of yours, like the string. And then you moving a bit more, and then at the end you are calling this printf function with two things basically. One carrying out your this whole string thing, and the second thing basically considering your sum variable, right? Then when you do this call printf thing is done, then again you're supposed to move the 0 to EX register, which is basically a return register, and then you do a few more this stack setup and changes, so that you can go back to your caller function, and then you leave this particular function and then return, which pops back the return address and go back to wherever it came from, right? So I think I hope now at least we know how to read a source code and the assembly code side by side. So let's recap what we did in the first x86 crash course video. We saw how a simple C program turns into assembly with instruction, directives, label, and comments. Then we talked about code versus data sections like .text or .ro data. We also saw how the Intel and AT&T syntax differs. We also saw two different versions of x86 instruction representation, assembly level representation and a machine level representation. We also looked at many important x86 instruction like add, sub, jump, compare, test, etc., etc. And then we also look at how to actually read source code and the assembly code side by side. So for the next video, part 2 of the x86 assembly course crash course, we are going to look into detail how this the machine level representation of x86 look like, and we are going to walk through case by case example, byte by byte. So thank you for watching this video. If you find this helpful, please consider liking, subscribing, and dropping a comment. Thank you very much. See you in the next video.